All right, everyone, welcome. In this explainer, we're going to do something pretty cool. We're going to follow the entire journey of a single UV photon. I mean, from the moment it's just a packet of energy hurtling through space to the second it slams into our patient's DNA and all the way through to the practical, real-world advice we give in our clinics. So let's dive right in.
So here's our game plan. We'll start with the physics, the initial physical insult. Then we'll zoom into the cellular battleground. From there, we'll unpack the fascinating paradox of the immune system's response, look at the long-term chronic effects, and then wrap it all up with what matters most, mastering patient photoeducation.
Okay, first things first. Before we can talk about any of the biology, we have to understand the physics of the insult itself. What exactly is UV radiation? And crucially, how deep does it actually go?
Now, the sun is throwing a lot at us across the spectrum. But here's the key. The atmosphere acts like a filter. So for our clinical purposes, UVC is basically a non-issue. It gets blocked. What we're really dealing with, what's actually reaching our patients, is mostly UVA, and that smaller but very potent slice of UVB.
This right here, this is the one simple rule of photophysics that dictates everything else that happens. It could not be more straightforward. The longer the wavelength, the deeper that energy penetrates into the skin. Simple as that.
And because of that one rule, we get this beautiful separation of powers. Just think of it this way. UVB is like a short-range attack. It gets absorbed right in the epidermis. But UVA, that's the long-range missile. It bypasses the epidermis and dives deep into the dermis. This one fact explains so much. Why UVB is the main sunburn ray, and why UVA is the primary driver of deep dermal photoage.
Okay, so let's zoom in. The photon has made it past the stratum corneum. Now we're at the cellular level. How is that physical energy actually absorbed and turned into real biological damage?
You have to remember this. UV light itself doesn't do anything until it's caught. A molecule has to absorb that photon's energy, and that molecule is called a chromophore. This is the critical first step. It's the spark that lights the fuse for absolutely everything that follows. No absorption, no effect.
Now, the skin is packed with potential targets, as you can see. But when it comes to UVB and its most dangerous effects, the number one target, the most important chromophore by far, is DNA itself. The genetic code is in the direct line of fire.
So this is that direct hit. A UVB photon literally slams into the DNA helix, and it forces two adjacent pyrimidine bases to link up, forming these bulky, unnatural bonds called CPDs. This physically warps the structure of the DNA, creating a huge roadblock that messes up both replication and transcription.
UV, on the other hand, is much sneakier. It plays the long game. Instead of a direct hit on DNA, it gets absorbed by other molecules nearby. This absorption creates a cascade of highly unstable reactive oxygen species, free radicals. It's these molecules that then go on to attack the DNA. It's not a direct assault. It's damage by chemical shrapnel.
All right, now we get to one of the most elegant and frankly clinically relevant concepts in all of dermatology, the bizarre, contradictory relationship that UV radiation has with our immune system.
This is the million-dollar question, right? And the answer, which is the foundation for everything from a simple sunburn to how phototherapy actually works, is that it's profoundly both. It just depends on which part of the immune system you're talking to.
The best way to think about it is this. UV triggers a local riot while calling for a systemic ceasefire. Acutely, in the skin, damaged keratinocytes are screaming for help. They release these DAMPs, which rallies the innate immune system and gives you that hot red inflammation of a sunburn. But at the exact same time, on a broader scale, UV is inducing regulatory T cells and cytokines like IL-10, which basically tell the adaptive immune system to calm down, stand down, and ignore new threats.
And this right here, this paradox is the razor's edge we walk on every day. It's what we exploit and what we fear. We use those immunosuppressive effects to our advantage to treat things like psoriasis, but we also know that that exact same mechanism is what can allow a newly formed cancer cell to evade detection and start to grow.
So let's pull back. We're zooming out from the acute effects of a single sun exposure. What happens when this battle is fought over and over again, day after day for years and decades? What are the cumulative consequences?
Well, this is the textbook cascade, and it's really the perfect storm. UV light delivers this brutal one-two punch. First, it directly causes the DNA damage that leads to mutations in critical genes like TP53. And then, it cripples the very immune system that would normally be responsible for finding and destroying those mutated cells.
And here's the thing, this damage isn't just random cellular chaos. Oh no, it's incredibly specific. So specific, in fact, that it leaves behind a genetic fingerprint, like a calling card left at a crime scene.
I mean, this is amazing. When you sequence the genome of a squamous cell or a basal cell carcinoma, and you find these specific C to T transitions, or even more telling, the tandem CC to TT substitutions, that's it. That's the smoking gun. You are literally seeing the ghost of past sun exposures written into the tumor's DNA.
Okay, so we've got the pathophysiology down cold. Now, let's pivot to what is arguably the most important part of our job. How do we translate all of this incredibly complex science into simple, actionable strategies for our patients?
We have to teach this as a hierarchy. It's crucial. Sunscreen is not plan A. It's not the first line of defense. The most effective thing a patient can do is change their behavior. The second is to use clothing as a physical barrier. Sunscreen is the final step for the skin that's still left exposed.
So when patients ask you about mineral versus chemical sunscreens, this is the core idea to get across. The inorganic or physical filters, like zinc and titanium, they work like a shield, mostly reflecting and scattering the UV away. The organic or chemical filters, they work more like a sponge. They actually absorb the UV photon and convert that energy into a tiny, harmless amount of heat.
And here's a great way to manage patient expectations about SPF. An SPF of 30, when applied correctly, blocks about 97% of UVB rays. Doubling that to an SPF 60, it only gets you to about 98%. The higher you go, the gains become really, really marginal.
Okay, listen up, because this is probably the single most important clinical pearl in all of photo education. The SPF value on the bottle is based on a lab test using 2 milligrams of product per square centimeter of skin. But in the real world, nobody does that. Most people apply a quarter to half that amount, which means the actual protection they're getting is way, way lower than what they think. Application amount is everything.
So I want to leave you with this final thought to chew on. We know that chronically sun-exposed skin is just a mosaic of mutated cells. So this really reminds us that photocarcinogenesis isn't a simple switch that gets flipped. It's a long, drawn-out war of attrition. A story of constant damage, imperfect repair, and failed immune surveillance, all playing out over the course of decades. And understanding that complexity, that's the real key to mastering this field.